So we am I audible?
Yes.
Okay. Good afternoon, everyone. So today is the 11th interaction session on structural vibration. My name is Devashish Panda. I am a Prime Minister Research Fellow at IIT Guwahati. So for this semester, I have been allocated to this course as PMRF TA. So this course is instructed by Professor Arunasis Chakraborty, IIT Guwahati. So today, what we do? We will go through the continuous system where we will first see the free vibration of beams, where we will solve both the transverse and axial vibration of beams. Then we will talk about some mode shape regarding the continuous systems, and then we will move to the force vibration. And simultaneously, we will solve the problems and tutorials which will be helpful for your assignment solving sessions. So let's start quickly. Um, so during uh, last interaction sessions, we have been dealing with the discrete systems where we use the spring mass despot systems, right? Just recall, we have actually discretized the system as per the generalized coordinates or as per the degrees of freedom. That means we have defined the masses, right? So for the single degree of freedom, we can define this as the degree of freedom, and subsequently for multiple degree of freedom systems, we can add this model, and we solve the shear frame or shear building model using the discretize mass concept. So we can discretize any continuous system, that is not the problem, but there are still we haven't talked about the continuous systems where, like, during the first interaction session, I discussed that we can model the mass as a lumped mass where, like, we have a cantilever beam. If we have a cantilever beam like this, so either we can model this as a point mass over here as a single degree of freedom system we can consider, and spring and damping properties. On the other hand, if we on the other hand, also discussed that we can model the mass as a continuous mass where that as per the length the mass will vary. That means the mass is denoted per unit length, right? So today we will precisely go through the continuous system, how we can solve the entire dynamics of a continuous system. Say for example, instead of any spring mass system, we have a simply supported beam. Say for example, we have now a simply supported beam,
This is
and
some.
some, yeah, Nandalal. Yeah, are you want to say something?
No, sir, no, sir, no, sir. Sorry.
Oh, yeah, no issue. So if we have a beam like this, say X and Y, and some forcing function is applying uh, over the beam, and the beam has, say, length L, and the beam has mass, say for example m bar. This is the mass per unit length. Now the thing is, here we know precisely one mass is there because we have modeled this as a lumped mass system or a discrete system, so we know the position of the mass. Now here we can have multiple degrees of freedom corresponding to each of these position of the masses. Okay. So that means we can have, if we consider that in number of points we will consider, then there should be a number of degrees of freedom, and corresponding we know that corresponding in number of natural frequency will come. So how to solve this type of continuous system, or how to capture the dynamics of this continuous system, we will see. So first, you know, for the transverse loading, if we want to consider the transverse loading case, so for continuous system, if we have this beam, say for example, we have the beam of length L, which have mass m bar. This is the mass per unit length. We have the flexural rigidity property EI, and one loading is applied on this continuous beam. So we will solve this system using the approach of free body diagram. So what for that, how do we will do? We will first consider a elementary strip or elementary area at a distance x from, like, from and A. We have considered an elementary distance dx at a distance x from, say for example, from A side. Now we will draw the free body diagram of this element. So obviously the loading is acting on the beam. So obviously shear force and bending moment will come at each section of the beam. From the basics of the structural analysis, we know that, right? So if we draw the free body diagram of this element, so what will we found that first one shear force is acting upward, and on the other section we will have the shear force V plus the incremental increase of the shear force over this length, right? So we have two forcing components, two shear forces acting on two sides. Then we have the external force acting on this element, say total force like F or P x comma t. That means the force will vary with time and the length also. So say for example on this elementary strip we have the intensity of load P and the width of this elementary strip dx. One more thing we have on this elementary strip, that is the inertia force. Now, inertia force, what is inertia force? We know like mx double dot. So m here we have defined the mass per unit length. So total mass over this strip will be m bar into dx. Now multiply it with double derivative of the displacement. You will get the inertia force. We will acting downward, and it's a beam section. Shear force acting on the both sides, so obviously it will be subjected to some bending moment on the both side. So if we consider the bending moment m acting on this side, so obviously on the other side it will be m plus the incremental increase of this bending moment with that elementary strip. So now we have all the information about forces and moment. Now we can apply the equilibrium condition to get the equation of motion for this no, or the governing differential equation for this beam or for this entire continuous system. So how we can do it? So as I said, we are now talking about the transverse loading cases. We can have axial loading also. We will discuss in a minute. So now, as there is no axial force acting on it, so we can directly use summation of Fy is equals to 0. Now take a proper sign convention, say upward positive, clockwise positive, downward and anti-clockwise negative. You can consider it, and we can easily formulate the governing differential equation for the beam, right? And it will look like V minus V plus incremental increase of V with that element plus like if x of t, the portion of the forcing function acting over that minus the inertia force is equals to 0. Now we know from the basics like m is equals to ei from the beam bending theory, d square y by x square, and the shear force v is nothing but del m by del x. That means ei del qy by del x cube. Now, if we replace all these things within that equation, we will find out the governing differential equation for the transverse loading case for the beam, and that is ei d24y by dx4 plus m bar. M bar is nothing but the mass per unit length, d2y dt2 is equals to the forcing function. So this is the uh, you know uh, uh, partial differential equation. We need to solve this, and once we have solved it, we can easily find out the responses. So till now what we have done, we have just constructed the partial differential equation or the governing differential equation for transverse loading case of a beam. Now if we consider the free vibration case, so obviously for the free vibration case we know like the vibration which is initiated by the initial condition, but it is completely free from the influence of the external loading. That means that f or px comma t should be equals to 0. So first let's consider the free vibration, the undamped case. Then we will add the damping. So undamped case, obviously the differential equation will look like ei d24 by dx4 plus m bar d2y dx2 is equals to 0. Now, so this is actually the equation for the undamped free vibration case of a beam for the transverse loading case. Now we need to solve this equation to get the responses. Now it's a PD. There are different ways to solve the PD, and your course instructor has recommended use the separation of variable scheme. Separation of variable scheme. So for the separation of variable, what we will consider, let's take a function y x comma t. We separated it into two functions, phi x function of the length and y bar of t function of time. Now if we substitute this information y x comma t to this equation, this PDE, say for example this PDE is equation number A. So what will we get? We will get a nice long expression for the free vibration case. So this is ei y bar of t d24 phi of x dx4 plus m bar phi of x d2 y bar by dx2 is equals to 0. Right? Now if we simplify it, we will get ei phi, its fourth time derivative with respect to x divided by m phi of x is equals to minus y bar double dot of t and y bar of t. So y double dot of t, that means the time derivative, double time derivative, that means the double derivative with respect to time, and this 4 Roman 4 is actually how many times we make the derivation with respect to x. That means we have two variables, one variable with respect to the length or the catered the properties of the length, and one variable which catered the properties of the time. Now look at this expression. So if this the uh, this hand side of the function is a, or the variable is a function of x, that means the length, and on the other hand side this is a function of time. So if these ratios are constant, so obviously we can consider a constant over it. Say for example we are considering the constant as omega square or omega n square. So if we consider that, then if we take the first part, I mean ei phi, 4 times derivative with respect to x divided by mass per unit length phi of x is equals to omega n square. Now simplify this equation, we will get this phi 4 time derivatives with respect to x minus a, actually we have simplified, a to the power 4 is nothing but m bar omega n square by ei, 5 times of x is equals to 0. Now similarly, if we equate the second part, that means minus y double derivative with respect to time over y bar of t is equals to omega n square, then we will find out this expression y double dot of t plus omega n square y bar of t is equals to 0. Now we have these two equations, right? One as a function of x, one as a function of time. Now recall, what was the free vibration equation for a single degree of freedom system? X double dot of t plus omega n square, or undamped free vibration case, x of t is equals to 0. Now we have similar kind of expression here, right? So now if we consider this as a free vibration case, and for this free vibration solution we get the solution x of t, just recall we get the solution in the terms of a cos omega n t plus b sin omega n t, where a and b are the constant which we can actually find out from the initial conditions. What are the initial conditions given? From that we can find out the solution. So we have one, that time dependent function we have already derived. Now for the shape, related function phi of x we need to evaluate. That means we need to work with this equation. So for the shape function, if we consider the solution will be phi of x is a terms of harmonic c into e to the power sx. Now, if we consider this as our trial solution, so what will be phi dot of x? We can easily find out what will be phi double dot of x and what will be phi fourth of x and so on. Now, if we find out these expressions and put it back into this equation, say this is a or this is b, say for example, if I consider it b, if we put it back in this equation, we will find out s to the power 4 minus a to the power 4 c sx is equals to 0. Now, what we have considered that c e to the power sx is the trial solution, one of the trial solutions, so it cannot be 0. Otherwise, we cannot have any kind of solution, or that leads to the trivial solution. So we will left with this equation s to the power 4 minus a to the power 4 c e to the power sx is equals to 0. That leads to s to the power 4 minus a to the power 4 is equals to 0. That means we have four roots of s. S will be plus minus a and plus minus I, the complex conjugate of a. Now, once we have all this information of s, now we can expand this equation. The phi of x, because we have four roots, so phi of x we can write it down c1. For the trivial solution, what we have considered that phi of x is c e to the power sx, and s we have four roots. So now we can expand this equation like this: c1 e to the power ax plus c2 e to the power minus ax plus c3 e to the power ix. That means four roots we are actually incorporating here, because we will going to use that Euler equation e to the power plus ix is equals to cos hyperbolic ax plus sin hyperbolic ax, and simultaneously e to the power ix is equals to cos ax and I sin ax. Now, finally, we have the expression for the phi of x. That means the function which cater with the length or the shape of this continuous system. We very often we call it a shape function. So we will see how we can derive the shape function and all these things related to this continuous system. So now we have this expression for the variable which cater the length factor, and also we have the solution for the time dependent variable which cater with the responses that will change with the time. Now, what we need to do for these cases like continuous systems, we can have two kind of conditions, or two kind of say one is the boundary condition. That means either the beam can be simply supported, that means both hand can be hinge or roller, it can be free, it can be fixed free. That means we have distinct boundary conditions, and also the loading is there, so we can have the initial condition. So this boundary condition and initial condition, using that two factors, we can easily find out what will be the value of the total responses. So say for example, for now we are considering that both end simply supported. So for the both end simply supported, what we know that the displacement at this true end, that means x is equals to 0 and x is equals to L, the displacement y 0 comma t should be 0. Also y 0 comma or L comma t should be 0, right? Now tell me, for a simply supported beam, for this two end A and B, the moment is also 0. So we can write out the boundary condition with respect to moment. That means moment at L is equals to 0 is 0, and moment is L equals to L, x is equals to L is equals to 0. So we have four boundary conditions. Now we can use these four boundary conditions to solve these four unknowns like A, B, C, D. Great. Now instead of this simply supported beam, we can have free condition, we can have fixed free condition. Now as per the boundary condition, whatever is provided or given, we can look into it and go for the unknown solution. So for here we are considering both ends simply supported. For the both ends simply supported, obviously the displacement at x equals to 0 will be 0, the displacement at x equals to L will be 0. Obviously the moment, bending moment at x equals to A, that means x equals to 0 is 0, and at x equals to L, M is still 0. So now apply this boundary condition. So at x equals to 0, we can have phi of 0, that means use this equation, equation number C, and put all these boundary conditions. So what we will have? We have phi of 0 is equals to 0, phi double dot of 0 is equals to 0. Phi of 0 is equals to 0 from the displacement boundary condition, and this is from the moment boundary condition. Again at x equals to L, similarly we will find phi of L is equals to 0 and phi double dot of L is equals to 0. Now put all these values with that equation at x is equals to 0. So what we will found? Phi 0 is equals to a into 0 plus b into 1, because b cos, c into 0 again, and d into 1. And if we differentiate this function, double differentiate this function with x and apply the moment boundary condition, what we will be found? This expression phi double dot of 0 is equals to a square minus a into 0. We will only left with the cos terms, right? So b and d. So from these two equations, d and e, we will found b plus d. So from this equation we get b plus d is equals to 0. From this equation we get minus b plus d is equals to 0. That means we can say b is equals to d is equals to 0. Now once we have this, we can easily construct the shape function or the variable which catered the length or lengthwise variation of the beam. We can easily find out what will be the phi of L and what will be the phi double dot of L. Now from this expression we can easily find out that we have sine AL, so that part cannot be 0, because if A will be 0 we will not get any kind of solution. So obviously that part needs to be 0. So if that part needs to be 0, we find out that that will be big C. C should be equals to 0, because hyperbolic function cannot be vanished from a non-zero arguments, right? So that should be 0 either, or that should not be there. Now once we have this, and if we simplify this, we will find out that a sine AL is equals to 0. That means sine AL is equals to 0, which actually leads to like an of L is equals to n pi, where n is equals to 0, 1, 2 from the basic mathematics. So now we have solved the like or we have found out the expression for phi of x. We have found out the expression for y of t, and we were solving this equation using this separation of variable scheme, where the total response or the total displacement is a function of the length and a function of time. So we have two information. So what will be the total response of this thing? What we need to do? We just need to sum them up. N is equals to 1 to n, or I is equals to 1 to n. How many modes we have, or the natural frequencies we have, summation of that multiplied by phi of x, y bar of t. So precisely that thing has done here. So y x of t, we can write it down like a, because phi n of x we can find out that is nothing but a sine n pi x by n. So the expression looks like a sine n pi x L, a n cos omega n plus b n cos omega n t. Now, if we consider, we multiply this a multiplied by an and a multiplied by bn, because a is my constant and this A and Bn are also constant. So take is that this is one constant at a time, and this is summation of one constant at a time. Now we need to solve this constant. How we can solve this constant? Now these constants are with respect to the time variable. That means we now need to use the initial conditions of this case. So there may be different kind of initial conditions may be there. So let's consider the initial condition, the displacement x at time point t is equals to 0 is nothing but rho, that a function of x. Say it's a function of x. That can be different kind of function we can provide to that system to get the responses. So this is the displacement at time equals to 0, at t equals to 0, and this is the velocity at t is equals to 0. Now once we have put all these values in this equation, what will we have? We have first this an sin n pi x by l is equals to rho of x, and for this part bn cos omega nt, or omega n sin n pi x by l is equals to psi of x. That means what we need to do first, to find out the an, you just directly can put the boundary or the initial condition y x comma 0 directly, and to incorporate this, what you need to do, you first need to differentiate it with respect to time. Then you need to incorporate the initial condition, that dy x comma 0 over dt is psi of x, is a function of x. So once we have do this, or once we have completed this, we will find out the value of an and the value of bn. So an looks like this, 2 by l rho of x is a function which depends on the initial condition, sine n pi x by l into dx. For the bn, again we have 2 by omega n l 0 to l psi of x, that means a function which depends on the initial velocity sine n pi x by l. Now for this system, we can easily say that the natural frequency of the system, already we have discussed the natural frequency of the system, that n square here, omega n will be nothing but a l square ei m bar l to the power 4. So because we have considered this constant omega n square, now if we simplify this equation, we will find out that omega n is nothing but a l square ei m bar L to the power 4. And if we consider that this part is nothing but C, some constant or some variable, which we will calculate later. So C under root of EI m bar L to the power 4. That means if we have the information about the natural frequency, the length, the flexural rigidity, we can, or and mass per unit length, we can easily calculate the natural frequencies of the system, and subsequently we can do the the responses. We can find out the responses. So from here, now if I want to write down the complete expression, we can easily write it down like here. Just replace the value of an and bn and get the initial condition, what will be the functions we will use for the initial condition. If you have all these things, you can easily calculate what will be the total response due to that modes, whatever we have found out for this system. So for the simply supported case, so we are actually talking about, till now we are talking about the free vibration case of a simply supported beam for the transverse loading condition, where first we have formulated the equation of motion, which is a form of PD. Now we have solved the PD with the help of the scheme separation of variable, where we have considered two variable phi of x and y of t, or y bar of t. One is a function which cater the length factor, and one with depend or with which depends on the time, or the time variable. Then we have solved this phi of x and y bar of t. So phi of x we call the shape function. Here we have solved the phi of x. Ultimately phi of x look like this. That means phi n of x is nothing but a sine n pi x by l. And for the responses, time responses, we have already the equation this. y of t is equals to a cos omega n t plus b sin omega n t. Now, if we add them, we will get the total response. So first, to get the total response, first let's talk about the mode shape. So what will be the first mode, second mode, what will be the natural frequency, and all these things. So we are talking about a simply supported beam subjected to some forcing function, say f x comma t. It has a length L, mass per unit length m bar, and the flexural rigidity A. So what will be the natural frequency for this system? Already you have derived. You just please recall this formulation because you will need it during your examination to calculate the natural frequencies of the continuous system. Okay, the EI, the mass, for which mode you need to calculate, all of the things will be given. You just need to do the calculation. So for that, you just need to recall this equation. So omega n is nothing but Cn under root of EI, mass per unit length, L to the power 4, and Cn is nothing but for this n square pi square. And for the shape function, we have seen the shape function is nothing but some constant multiplied by sine n pi x by L, right? So some constant we can use different kind of function also. So mainly that will be influenced by this harmonic. So the first mode shape, if we uh, write n is equals to 1, the first mode shape will look like this. So this is for n is equals to 1, the first mode shape. Okay, what will be the second mode shape? If we put n is equals to 2, we will have this mode shape. If we put n is equals to 2, and at the end point it will it will change its sign. Now for the n is equals to 3 and for n is equals to 4, we will have different mode shape for this kind of beam problem and for the transverse loading case. Now if we have these two equations like phi n of x and y of t or y bar of t, or in short, if we have this total expression like sine n pi x by L an cos omega nt plus bn sin omega nt, we can easily solve the response or the total response of the continuous system. Now using hand or pen or paper, you can go up to 1 or 2 time step, but using the MATLAB, if you write down all the equations properly, we can solve it within few clicks. We will see how we can do it. So that is the free vibration case for the simply supported both in like simply supported case, and we have seen what will be the natural frequency, what are the mode shape information of this beam. Like from here you might have this kind of question like uh, for a beam for a beam for a beam, the mass per unit length is given, ei is given. Okay, now we till now we have considered this loading case is 0 because we are considering the free vibration case, right? We will see the force vibration case. So for now we are considering the free vibration case, that means the forcing function is 0. So they will ask what will be the natural frequency for the first mode omega 1, what will be the phi 1 of x for that case. If all this information are provided, you can easily calculate it. Or if asked like for the first mode and for the say third mode or fourth mode, what will be the ratio of the natural frequencies, you can easily find it out, right? Like what will be the ratio, say tell me what will be the ratio for this case for say n is equals to 1 first mode, or say n is equals to 2 and n is equals to 4 fourth mode. What will be the ratio of the natural frequency? That means omega 2 and omega 4 for the simply supported beam with simply supported beam in free vibration case. Tell me, Bob, what will be the ratio between that two? Same beam. Say for example, we have a beam. Yeah, Bob.
Yeah, you mean which n is equals to what? Two and what?
N is equals to 2 and
And
4.
three
I am talking about second mode and fourth mode. What will be the natural? What will be
and
the ratio between the natural frequency between second and fourth mode of this beam? Say L, length L, EI is given and M bar is given. That means same for the beam. So what will be that?
that will be 1/4.
Yeah, that means in 2, that means 2 square divided by 4 square. That means 4 divided by 14, that means 1 by 4. Great. So I hope you have a similar kind of question in your assignments. So it's very simple, but just you need to recall the equation and the tricks. Okay. Say like I'll just show you. Yeah. This problem. Find out the ratio between the natural frequencies of sixth mode. This actually I have changed the question. In your question, something second or fourth mode will be there. Sixth mode and second mode for a simply supported beam. So it's nothing but your n square by n square because all the property will be same. So omega 2, omega 4 or omega 6. Here I have considered 6. So 6 will be calculated like this. Get my point? Okay. And also they might ask for the natural frequencies. Great. So from this section, what you need to recall these two parts. What is the natural frequency? What will be the mode shape information? So here we have considered a sinusoidal function to calculate the mode shape, but precisely there are ways to calculate the mode shape. Like if you have the knowledge of the finite element method, their shape function to calculate the shape function, we have different kind of method, Rayleigh-Ritz method, Rayleigh method itself, and all these kind of things. But these methods are irrelevant for now. We'll stick to these things. Okay. So now, if we have both and free, what will happen? If we have both and free, so we have two expression. One is for phi of x, one is for y bar of t. Y bar of t is nothing but a cos omega n t plus b sine omega n t, and this is the function with respect to time. This is the function with respect to the shape. So previous example we have seen for the previous example we have seen for the simply supported case, that means both end like hinge, one end hinge and one is this roller. Now we have both end free, both end is free, say a and b will be free. So what will be the boundary condition? Tell me, what will be the boundary condition? You can easily calculate the boundary condition, you can easily sense the boundary condition. What do we need to find out? What will be the moment at x is equals to 0 and moment at x equals to L? What will be the displacement at x equals to 0? What will be the displacement at x equals to L? Now once you have this information, you can easily put it back into this expression, because we have four boundary conditions and you have four unknowns to solve this equation, the mode shape. Because we have seen for a beam case, for the shape function we can have four roots, plus minus ai, and here plus minus a and plus minus ia. That means two complex conjugate of these two, and the equation finally looks like this, which contain four unknown variables, which actually we have solved using the boundary conditions. That means the shape related function solved, the unknown related to the shape related function solved using the boundary conditions, and the unknown related to this time variable or the time function y of t is solved using the initial conditions. So similarly for this case we can solve it. So if we just simplify this, we will have this two equation, and finally leads to for the trivial solution, a will be equals to b equals to 0, but we are not looking for the trivial solution. So what we will have from these two equations, say 3a 3b, the determinant of this will be 0. So if we take the determinant of it is equals to 0, that means if we simplify it, cos al minus cos hyperbolic al minus 1 is equals to 0. Finally, we can write like a will be equals to nothing, cos a l minus cos hyperbolic of al divided by sin al minus sin hyperbolic of al multiplied by b. So a should be equals to this. Now we have this phi n of x equation. Previously we have the information of a and b. Here we have seen that what will be the value of a in terms of b. So now if we substitute all these things, so I have jumped some step. What you need to do, you just need to write it down the steps. It's very simple and straightforward. Just step by step you write it down, and you will find out that finally that phi n of x, the safe function, uh, for this free case, we will have cos hyperbolic anx cos anx minus sigma, its simplification version, sigma of n is nothing but cos anl minus cos hyperbolic anl divided by this sine and sine hyperbolic thing multiplied by this part. So finally, we know that omega n is nothing but anl square under root of ei by m bar l to the power 4. For the simply supported case, both end hinge and roller, we have here an into l square pi square into n square. We have found it out. Now here for this case, an we know from where we can get the an, already derived the expression for the an on the previous example, like what is the value of a. Yeah, from here a we can express this. Also here also we have expressed for this equation anl is equals to n pi, and finally n will be n pi by l, and subsequently n square pi square we have found out. So similar way we can do this for this an l square ei m bar l to the power 4. And we need to calculate separately for each cases. So for the simply supported beam, not for the simply supported, for the free case and for transverse beam bending case, we have this you know this as a natural frequency term. Now this an very often will be provided to you if we need to calculate the value of omega n, because this an we need to primarily calculate it first, then we need to incorporate within the equation to calculate the total response of the thing. So if some question will ask to find out natural frequency of these things, that an part will be given, an l, and the information about mass per unit length and corresponding the flexure rigidity, all the information will be given to you. Now similarly we can have the modes of information, like here we can plot it over here, but what you need to do, you just need to write out this function within MATLAB, find out the natural frequencies for n is equals to 1, n is equals to 2, n is equals to 3, and solve for this phi of x, plot it, you will get this mode shape like this. So I will not discuss detail here, rather we will solve these things using MATLAB, that will be helpful for us. So for us, like what kind of questions may come from here, we will look into that. So till now what we have seen, like what will be the equation of motion for a beam or for a continuous system, and for the continuous system we have considered the beam here. So for this case, so we are considering first the free vibration case. That means the forcing functions we have considered f of x comma t is equals to 0. The beam has length L. What will be the total response y x comma t, and what will be the natural frequency for it, we have found out. Now we have considered particularly for the transverse loading case, because recall EI d here d4y into dx4 plus m bar d2y by dx2 is equals to f of x comma t. This governing differential equation we have derived considering the transverse loading, because we have considered the equilibrium equation in the transverse direction. Transverse direction, what are the transverse direction? Okay, let's quickly discuss some very basics point of a beam. Okay, just quickly, then we will move to this free vibration of axial deformation due to the axial deformation. Say for example, this few basic things. So if we have a beam or an element, 3D element, okay, so if I put the axis, say this is y, this is x, and this is z, this is the length. So tell me, which one is the longitudinal axis and what are the transverse axis here? Tell me, which are the longitudinal axis and which are the transverse axis? Say it has a depth d and width b. Tell me, someone, please, which axis we call the longitudinal axis, which axes are called the transverse axis, which we call cross section, which we call shear force, which we call axial force. Just clarify these definitions one by one. So first tell me, for a beam,
X,
yeah,
X-axis is longitudinal axis.
x is the longitudinal axis. Why or how you can tell this axis is the longitudinal axis? Because we considered for a 3D object the bigger axis, we call it the length, right? So along the length, the axis we call the longitudinal axis, and the other two axes perpendicular to it we call the transverse axes. So this is the longitudinal axis, these two are the transverse axis. Now whom we call the cross section of the beam, we very often use this term cross section, cross section, cross section. Whom we call the cross section? Then we will come to the shear force and axial force thing, and also bending moment and twisting moment. All the concept we will clear within 5 minutes. Yeah, cross section. Please define the cross section, Bob. Sovik, anyone?
When you take a section through the beam, like along the y-axis, you cut a section and then you look at it from the side, from the Z point of view.
Okay, so now I will, make the question simpler. Like, let's consider this A, B, C, D. This top part is also a section. Let's consider C, D, B, A. This is also a section. In which section we call the cross section? Now tell me, Bob. Even if we can cut this as per the z axis, we can have here also a cross section. So whom we call a cross section? We have now longitudinal axis, transverse axis. Whom we call the cross section? Yeah,
Section perpendicular to the axis is known as cross section, sir.
yeah. That's the precise definition. The axis perpendicular to your longitudinal axis. Not, you don't call it x axis.
Okay, okay.
Longitudinal axis.
Here it is x-axis
Yeah,
is the
here it's defined. Here we call the x-axis. So the section perpendicular to the longitudinal axis are called the cross
yes,
sections.
yes.
Yeah. Now tell me, whom we call the shear forces or the transverse forces, and whom we call the axial forces. So the forces acting along the longitudinal axis, we call them axial,
Axial forces. Yes.
and all other forces which are acting corresponding to the transverse axis, we call the transverse loading or the shear forces. That means this kind of forces can be
Yeah. Yeah.
shear forces. I can apply the shear forces from this direction because this is also the transverse direction. We can apply the shear forces from the bottom also, right? So shear forces, that means the forces which are acting perpendicular to the longitudinal axis or parallel to the transverse axis. Get my point? The
Yes. Yes, sir.
forces acting perpendicular to the longitudinal axis or parallel to the transverse axis. Now tell me, due due to what this beam bending will occur? Due to the transverse loading, obviously. Obviously, due to the transverse loading, the beam bending will occur. Yes or no? Is there any doubt? Like any kind of shear force will cause the bending. Either this kind of from this direction, the beam can bend. The beam can bend like this. If I apply shear forces from this direction, if I apply the shear forces from up to down, the beam will bend like this. And consecutively, in that direction, you are applying the load, the beam will bend consecutively. So that means the bending moment. Now come to the bending and twisting moment concept. So bending moment are generated due to
Air force.
transverse loading.
Okay.
Yeah. Now transverse loading, or we can say the loading perpendicular to the longitudinal axis, right? Now one kind of moment we have again, that is we call the twisting moment here. Now look, the twisting moments, that means the bending moments are with respect to the transverse axis. The moments with respect to the transverse axis we call the bending moment, and the moment with respect to the longitudinal axis we call the twisting moment, right? Like just fix that portion, apply the moment about the,
The twisting moment related to torsion.
yeah, it's torsion. Twisting
Yes.
twisting will
Yes.
happen, it's torsion, no? Obviously
Okay.
torsion. But
Okay.
twist, it will give the phenomena or the twisting phenomena to the beam, not the bending phenomena. Am I right?
Yes, sir. Yes, sir. Yes, sir.
So the twisting moments are with respect to the longitudinal axis. Rest are the bending moments. Whatever the moment with respect to the transverse axis is coming, we call them bending moment. That means we can have the bending moment mz, we can have my, but this mx will be the twisting moment or the torsional part, right? So
Thank you.
this is,
Thank you, sir, to clarify such a very good concept.
yeah, it's the very basics of civil engineering, and everyone should know this concept. Otherwise, how these loads will affect the material and the shape and the geometry, we will not have the clear idea, right? So these things must be clear at the very beginning. Anyway, and as per this axis the stresses are defined, like normal stresses, longitudinal stresses, then on the principal axis the principal stresses. So once you have cleared that basic concepts, all the thing will be fall in proper path. Okay, now here, till now we were solving the transverse loading case for the free vibration case. Now we may have the axial loading. So for the axial loading we need to solve the governing differential equation. Now it's a finite element problem. Like if we have a simply supported beam, or a beam, say for example we have a cantilever beam and a axial force is applying here. Now what will be the case? So for the axial deformation, the governing differential equation look like AE. I'm not derive this expression. It's a very basic expression. If you look for any finite element book, what is the governing differential equation for axial deformation of beam, you will find it out. It's simple. They
Uh,
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 yeah, Bob, you want to say something?
Sorry, I was doing something. Sorry.
Yeah, it's okay. So similarly, what we have done for the transverse loading case, for the transverse loading case, recall what was the governing differential equation: ei d24 y by dx4 plus mm, just forgot this m bar d2y dx2 is equals to f of that. So for the axial loading case, similarly, the governing differential equation will look like this. Now for this we can have the solution u here. U of t is the the variable which cater with the length, and we have one function for the time variable. And the process of derivation is quite simple, like take the solution, then what you need to do, you just need to differentiate it with respect to time and differentiate it with respect to x, and then substitute this within this equation. So finally, once you have substitute this, you will get this equation: d2u by dx2 plus rho is the mass per unit length, or the density of this beam, whatever you want to define. Omega square by e u is equals to 0. So finally, this equation, just recall, double dot of double dot u double dot x comma t plus rho, or simply we can simplify this equation like this, some constant lambda square into u is equals to 0, where lambda square we have taken rho omega square by. Now we can find out the general solution. First we need to find out the general solution with respect to x, then with respect to t. Once we have all found out, we can find out the natural frequency of this system also. And the natural frequency for this system, here all the derivation for this, like cantilever beam in axial vibration, I have write it down. For general solution, we have taken it like as a harmonics free vibration case, a cos omega in t plus b sin omega in t. So instead of omega, we have considered that lambda factor. The constant factor over here is lambda. Now recall, for this transverse vibration case, we have considered this as a to the power 4, and here lambda square. Similar kind of constants we are taking and solving the equation. Now once we have solved it, the omega n natural frequency for the axial vibration case, I think the axial vibration case has not been covered in your course, but still for the sake of completeness, I am giving that, like 2n minus 1 by twice l into pi. So like this is the expression for natural frequency of axial vibration of cantilever beam. So once we have this expression, we can easily find out what will be the omega 1. Omega 1 will be root over E by rho. E, modulus of elasticity will be given, mass density will be given. You will know what will be the mode you are looking for. Say we are looking for n is equals to 1. So 2 minus 1 by twice L. That means we will left with only pi by twice L. So this is the first natural frequency of this cantilever beam for the axial vibration. What will be the second frequency? Omega 2 will be under root of E by rho. Now instead of n is equals to 1, you put 2. So 4 minus 1, 3. 3 by twice L. By this way, we can calculate the natural frequencies and corresponding mode shapes. Like for the mode shapes, even x is equals to nothing but c sine lambda n x, and lambda n we have already calculated. So for the first mode, this will be n equals to 1, this will be n equals to 2, this part 0.5 into L, and so on. We can formulate it like so. For this kind of cases, I will recommend just take a pen and paper. If that thing is relevant to your work, then take a pen and paper, do all these derivations and implement it in MATLAB and try to clear all the concepts. And if we were doing it for the sake of assignment solutions and for the exam purpose, then you don't need to look into that derivations, because the derivations are irrelevant to solving your problems. Your problems, the problems which will come will be very simple, not like related to that derivation. I will show you the problems. Like one problem I will already explain to you. It's simple, but you need to have this concept from where I am getting this informations and all these things. Now let's talk about the orthogonality, like mode shapes. For the when we have first discussed with the mode shape, we have discussed the orthogonality property of this mode shape. Like recall phi, if we consider this as a modal matrix, phi transpose m phi is nothing but the m, and this is ultimately become the identity matrix. Now phi transpose k phi is the modal stiffness, this is modal mass, and phi transpose C5 we have the modal damping properties. That means the orthogonality property already we have. That means if we apply this transformation, we will have the orthogonal matrices of these things. And also we have seen that phi n transpose phi m should be 0. Only phi n transpose phi n should be 1. Now we will see for this continuous system, this concepts of orthogonality works or not. Obviously it will work, because um, in similar way, or based on the similar assumptions, we have derived that mode shape. So obviously that orthogonal property will satisfy. So how we can say that orthogonal property will satisfy? We need to show that either phi transpose some function phi n should be 0, phi m transpose some function phi n is equals to 0, or we need to prove this, that for the same mode phi n transpose phi n, that means orthonormal property, that leads to the conclusion, okay, that modes are orthogonal. Like here we have considered two modes, phi n and phi m. So this is phi m and this is phi n for a simply supported case. Just recall first two modes. We have considered the first mode for the simply supported case, n is equals to 1, for this is n is equals to 2. Now what we need to do, we will actually apply the Betty's law. Now to apply the Betty's law, recall the Betty's law, what Betty's law said, like if we consider the inertia force at nth mode shape and multiply with the m mode shape, will equals to inertia considered at m mode shape multiply with the nth mode shape, right? Here the Betty's law is explained. Like so for that, what we need to do, we need to look for the inertial force acting or inertial force related to this. So we can easily calculate for this n is equals to 1, what will be the inertial force I m. So that will be nothing but it's related to this phi m is related to what? They're related to omega m. This is related to what? Omega n. Because we know, like, particular mode shapes are related to, or that what was the definition of the mode shape? Tell me. We have discussed many times the definition of the mode shape. Tell me, what is the definition of the mode shape? How you can define a mode shape? Then only you can have, like, why I'm writing omega n and omega n. Bob, what we can say, what is the mode shape? Mode shape is nothing but Nandalal. Mode shape. What is mode shape?
Shapes are actually, if we have, suppose that is a first degree, the here now, first mode, then both end will be node and
No,
antinode will
no,
be
no.
method.
Like just I'm asking you the question. What is the mode shape?
Mode
Define
shape,
mode shape. Define mode shape.
what I will say, mm, what will be the shape of the beam in that
Just forget the beam and all these things. What is the mode shape? No. Just with respect to some structure, you can consider any structure. Just forget the beam.
Displacement at each degree of freedom.
No, displacement is degree of freedom cannot be the definition of a mode shape. Mode shapes are the deformed shape related to particular natural frequency, and they are independent of time. That means they are the, just think like that is the time frozen screenshot of the displacement, time frozen screenshot of the displacement. Say for example, we have seen that for a single degree of freedom system or the 2 degree of freedom system, we have seen two modes. Say this is 2 degree of freedom system, we have seen the first mode will look like this, and the second mode somehow look like this. What are these two? These are the deflection pattern. Listen to me. Deflection pattern related to a particular natural frequency of a structure. Deflection pattern. Okay, it's not the deflection, it's the deflection pattern. That means the time frozen screenshot of the deflection, time frozen screenshot of the deflection. These are not a function of time, but the displacement response is a function of time. When we have the displacement y of t, when we multiply this mode shape with our q of t, that means we have some generalized response, multiply with that mode will give us the total response. So mode, what is mode shape? It's the deflection pattern of a structure related to particular natural frequency. If I look for the first natural frequency, omega is equals to 1 and omega 2. So if I want to calculate the response due to first natural frequency, we need to consider the first mode shape. If we want to combine them to, what we have learned on the modal combination rule, what we have learned, we just add the modal responses. So mode shape multiplied by the generalized coordinate. What are the generalized coordinates? That are the responses, generalized responses, multiplied by this shape. What will you get? Just recall, just try to imagine that, like, at each time point you will have this kind of shapes, but this is not a function of time. Okay, and mode shapes are particularly related to the natural frequencies. For the first frequency, we can have different deflection pattern of the structure. For the second natural frequency, we can have different deflection pattern of the structure. Deflection pattern, that means time frozen screenshot of the displacement or deflections. Okay, Nandalal, now clear? What is mode shape? Now define mode shape.
Yes, yes. Deflection pattern of the.
So of any structure,
Yes,
related to a particular natural frequency. Get the precise definition. So we,
yes, yes, sir.
why now understand why your definition was wrong.
Yes.
Why? Yeah.
Yes.
Great. So for this also we can easily calculate. So this mode shape is corresponding to omega m natural frequency. This mode shape is corresponding to omega n. Say we have considered 1 and 2. Say now let's indexing it as m and n. Now we can easily calculate the inertial force. If inertia is nothing but, we know, like omega m square m bar x into the mode. And for this also omega 2 m bar into phi n x mode shape. Now once we have the modal information and inertial information, now we can apply the Betty's law. Like Betty's law, what the Betty's law said, work done by work done by the inertial force on mth mode is equals to work done by mth inertial force acting on nth mode shape. That means the inertial force acting, or the inertial force calculated here multiplied by this mode shape, should be equals to the inertial force this multiplied by this mode shape. That means two work done should be equal. Now here we have these two, inertial force into mode shape. We simplify it, we will get this nice and short expression, omega n square minus omega n square 0 to L m bar x phi nx phi mx dx is equals to 0. Now omega m cannot be equals to omega n. Two natural frequencies cannot be same. So what we left with? We left with this part should be equals to 0. That means phi n multiplied by m bar x phi m is equals to 0, and that actually satisfied the orthogonality property. So we can now say, okay, for the continuous system also, the modes are orthogonal to each other. Great. Now we have left with the force vibration part. So for the free vibration, what we need to recall, like similar kind of free vibration equations, but here as we have considered the two functions to solve this PD, that means we have used the separation of variable scheme. So we have two functions, one is with respect to the shape, one is respect to time, that means one with respect to length, one is respect to x, and once we can solve it sorry, we can have the natural frequency and the total response in term of this. Recall single degree of freedom system, only we had this portion like y of t is equals to a n cos omega n t b n sin omega n t. Now this part comes from this modal information which we use for the continuous system. That means we can have n number of masses or points in each point, and if we consider each degree of freedom, then we can have, or we may have, n number of degrees of freedom. Okay, so say for example, the questions like this: select the orthogonal condition between two normal modes of differential frequencies. What will be the answer? We have just answered this: 0 to L phi mx phi nx m dx is equals to 0. Now here the dynamic response of a simply supported beam due to free vibration is expressed as y of t, is like separation of variable, is phi of x into z of t. Now the length of the beam is given. Select the correct statement. Now here the correct statement is related to what? Boundary conditions. Recall the boundary conditions. Simply supported beam, simply supported beams, that means your v, that means the displacement at x equals to 0, 0, v at x equals to L is 0, moment at x equals to 0 is 0, moment at x equals to L again 0. From there, from this moment boundary condition, what we have found out, phi of 0 is equals to 0 and phi double dot of 0 is equals to phi double dot of L is equals to 0. Just go back to that, we have already solved it. What is the equation? One second, just one second. Okay, boundary conditions, we are talking about the boundary conditions, so you will found it from just few minutes back. We just solved this equation. Where are they now? Oh, here, these two. Get it? So we'll have phi double dot of 0 is equals to 0 and phi 0 is 0 is equals to 0 and phi double dot of L is equals to 0. So as per the question, you just need to select the answers. Great. Now, before going to the force vibration part, let's quickly solve some more examples. Okay, just focus on that. Here, we have already discussed this. Find out the ratio between the natural frequency of sixth and the second mode of a simply supported beam. So for a simply supported beam, the natural frequency is nothing but n pi by L square under root of EI by m bar. So what will be, they said, what will be the sixth mode? Omega 6 by omega 2 will be, everything is same, so 6 square divided by 2 square, that means 9. Great. Now second example. The second example related to the forcing function. So first we need to go with the force vibration part a little bit, then I will come to it. Okay, so now let's say we just can just 5 minutes we will spend here. So now let's consider the force vibration case. Like here, like the question directly ask Mn. This is the modal mass, K and the modal stiffness. We just need to find it out from the force vibration case. So just for the few minutes, you just bear with me. Then we will solve this examples. So now we are considering the effect of the force also. That means we will have a forcing function too. So this was f of x comma t applying over the beam of length L, and it has the flexural property EI and mass per unit length is m bar. So the governing differential equation, just recall the governing differential equation: EI d2 d4y by dx4 plus m bar d2y by dx2 is equals to f of x comma t. And we try to solve this equation using the separation of variable scheme. Y of t will be nothing but, if we have nth mode, then summation of n is equals to 1 to infinity phi n x zn of t. Now similarly, if we simplify this equation and put it back into the first equation, we will have ei phi n 4 times derivative with respect to x multiplied by zn. Zn of t is the time dependent, that means the modal responses or the responses, generalized responses we can say, is equals to f of x. We are just simplifying this equation, so we will live with this equation. Now what we need to do, just multiply both sides with phi n of x and integrate 0 to l. So multiply by phi n of x multiplied by phi n of x, that means obviously that will be 1 transpose there, 0 to l, again here 0 to l. So if we simplify this equation, we will get this. So omega n squared zn 0 to l m bar phi n x dx is equals to phi m x f x comma t zn and phi n squared x. Now if we simplify this equation, we will have, like, we want to simplify in terms of that dynamic equation we are familiar with, like m n zn double dot of t plus omega n square mn, that means k mn zn of t is equals to fn of t. Now if I want to simplify this equation, say this equation is 1 and simply I have simplified this equation to 2. So what will be the quantity of mn? Mn is nothing but this part here. So 0 to l m bar phi squared dx. What will be the fn? Fn will be 0 to l phi n x comma t, function of x comma t and dx. Now finally, if we want to fulfill this equation or complete this equation, so that equation will look like zn double dot of t. Recall a similar type of equation what we have solved for the favorization case for uh, single degree of freedom system, or for the modal coordinates in uh, multi degree of freedom system. So this is called the modal mass. This is called the generalized force or modal force, and this is the equation of motion for the force vibration case. That means we only have a forcing component which is actually normalized with the modes of the system. So the governing differential equation for undamped force vibration look like this. This is the equation of motion for undamped force vibration. And if I want to consider the damping part, the equation will look like this: zn double dot of t. Here we have considered 2 eta omega n zn dot plus omega n square Zn is equals to Fn by T. So here eta n is nothing but the critical damping, right? And zeta n we know twice m omega n, right? Critical damping means I have defined the critical damping. What is the critical damping? The damping required to completely diminish the vibration from the system completely. It's not like few damping, 4-5% damping is there, so some diminishes is occurring. But if I want to completely diminish that, we need to apply the critical damping. So we have defined the critical damping and all this part. Just go back and see the video lectures, so you will find it out. Now we can able to solve this problem here. Now just pay attention to this problem. I have changed the data. You can I've changed a little. I will tell how you can correlate with your problem. It's simply, it will take 1 minute to solve your problem if you focus on that problem. So a concentrated constant load of 20 kilonewton is suddenly acting on the midpoint of a simply supported beam. Suddenly acting. So there is a simply supported beam and one concentrated load of 20 kilonewton is suddenly acting on this beam. Suddenly acting on this beam. That means suddenly acting on these beams means it will create the vibration, right? It will create the vibration. Uh, I will discuss some more
You know,
concepts. Yeah.
so in practical terms, does it look like when something fall on the structure or when there is a sudden collapse from the first building, or in practical terms, in real terms, what can you relate it to?
Yeah, it's sort of impulse force. Impulse
Okay.
impulse, and we have solved response for the impulse forces. Recall the Duhamel integral we have used to solve the impulse forces, generalized forces. It's sort of impulse. It will create the vibration on the system, right? It's an impulse. That means this force is
Okay.
acting suddenly for a small duration of load. Say for example, as per your context, right, we have a building and one suddenly one say for example there is a crane over here and this bob hit, right? So what it creates? It creates the impact force on it, but that impact will remain for a few seconds or for for minimum second or for small duration of second. So that will the impact. Now the impact force, we know the impulse response function to solve this impact, Duhamel integral. So considered as impact. But this, if this 20 kilometer load is constantly applying at the midpoint, will it create or will it create the dynamic effect of the beam, Bob? No.
Yeah.
No. So for example, if you have a building and some sort of like if you want to test it, like if some mass is falling over the top of the building or the side of the building, what you need to do? You need to go for the analysis with respect to the impulse forces, considering that forces as an impulse. Great.
All right. All right. Okay. Thank you.
That means the intensity of force and the duration of the force will give you the total magnitude of the impulse. Just go back to that generalized force where we have solved force vibration of a single degree of freedom system using Duhamel integral. There you can see that impulses multiplied by that duration we have considered, and then we have solved for the impulse response function, right?
Yeah. Yeah.
We are
Thanks.
seeing the new people over here. Anyway, okay, so they have left. Just this example, a concentrated constant load of 20 kilonewton is suddenly acting on a midpoint of a simply supported beam of uniform mass of 60 kg per meter. That means the mass per unit length is also given, that is 60 kg per meter. In your question I think this is 80 or something. Okay, just be careful with that. You just get the idea how we are solving these equations or the questions, so it will take few minutes to solve yours. And the length is also given, 4.5 meter. The mode shape of the beam is given as phi n is equals to sin n pi x by L, where n is the mode number. Consider the uniform flexural rigidity, EI is given. I already mentioned, like this data will be given and you will be asked for different quantities you need to extract, like frequencies, modal mass, modal forces, modal stiffnesses, and all these things. We'll see. So the length is given as 4.5 meter, not 5 meter, it's 4.5 meter. Mm, just let me correct it. Oh yeah, I will correct it later. Like this is not 5, this is 4.5 meter. And it will not save actually. Anyway, 4.5 meter. What is the expression for the generalized mass? We have just seen few minutes back. Generalized mass is nothing but 0 to L m bar phi n square into dx. That means corresponding mode shape you need to have the mass per unit length. If you have these two information, modal information and mass per unit length information, you can get the modal mass. Recall when we have solved that multi-degree of freedom system, the modal mass we can easily calculate using phi transpose m phi, right? Or phi n transpose for each component, phi n transpose n phi. We will get the each component of the modal mass matrix. Here also we will use that equation to get the masses. So for the nth mode here, for the nth mode we can have like the mode shape is given. So phi n square m of x dx. So m is given 60. So 60 I took outside the bracket because it's already given for this for this scenarios. Now we left with sine square n pi x by l dx. Now you just need to integrate this. So sine square x, you just separate it like 1 by 2 into 2 1 minus cos twice x, like that basic mathematics. Just convert it sine cos equations, and you will find it like 60 into 4.5 by 2, 135 kg. So for your case, what you need to do, you just need to like replace 60, replace 4.5, you will get the answer. Get it? But you need to recall this expression, and all the mode shapes for your purposes will be given in terms of this sine function, sine n pi x by l. So how to integrate that sine n pi l by x, or the square of sine n pi x by l? Please recall. This kind of questions will come in your so clear how to solve this problem? Yes or no? Bob?
So in this case, the n was replaced by what? What is the value of n?
What is the value of?
It's 1 minus 2 cos n pi x.
Yeah,
So
it's
I'm
like
asking,
cos to n pi x here, like n, like cos n pi. What will be the value of cos n pi? Is equals to n is equals to 1 2 3 4 5. What will be the value? So it will basically, that part will cancel out, so we will left with only dx. So we will have x, so we will have only 4.5. Great.
okay, okay.
As simple as that. That's why I told you, just focus on that question, you can solve it easily. Okay, you don't need to think about that. What is the value of cos twice n pi x by l, or twice n pi, cos twice n pi, cos n pi? What is the value of cos n pi? What is the value of sin n pi? You just need to recall these things. Okay, so this
Hello.
yeah,
Okay. This is general question regarding that generalized mass.
yeah,
For nth mode shape, right? This we are getting 135 kg, which means that in particular mode shape, no, this contribution of mass is 135 for the length of the beam.
yeah.
That is the meaning.
Yeah, so if here for the nth mode, the generalized mode shape is given like in a general form. Now, if you have the first mode, like in terms of numbers or in terms of the shape, actual shape, you can easily calculate the contribution from this mass. Like we have calculated that for the multi-degree of freedom system, what is the modal mass for if we consider up to fifth mode, it will consider 95% of the modal mass and all these things. So it's the general case, but particularly for like your question, for each mode shape, if I know the mode shape, like first mode shape. What is the first mode shape multiplied by the mass per unit density and integrated over the length, we can find out what will be the contribution to that mode particularly.
Okay. If that is the case, right? No, we have to see how many number of mode shapes here.
Here that kind of questions, they have not asked like how many modes you need to consider, but basically if we have a multi-degree of freedom system and if we have n number of modes, so n number of modes, we need to consider the modes up to which the 90% of the modal mass is considered,
Okay.
and up to the fifth mode this actually happened. Just 1 minute, I will show you the details because we just have discussed these things on the last interaction session. Just wait. And for the seventh mode also we can have almost 98%, I think, the modal mass. And how you can calculate this, just go through the previous lecture. I have explained how we can calculate the effective mass and how many masses we need to consider, or how many mode shapes we need to consider for a nth mode system. Like just few minutes, we have already discussed these parts. Where are the things, where are the things? Just let me go through it once. You just need to consider the mass which counteract 90% of the modal mass here. Just 1 second, I will share the screen. We already have discussed these parts. I think you have missed it somehow, but I suggest you just go through the just previous week lecture. Just wait. I will show you that part. 10, I think week 10 here. In the week 10 slide number, if you go to that slide number, here all these things I have explained and how we can calculate the modal mass participation and all these things, and we have solved few problems related to this also here. 90 to 95% of the modal mass, if we contribute it, like we need to, how many modes we need to contribute, it's like 90% of the modal mass, up to which mode that 90% modal mass is covered, we need to consider. So up to generally fifth mode the 90% modal mass is covered, and up to, if we go up to eighth mode, the 95% of the mass is covered. And the modal mass we can easily calculate like this formula. Li by mi, and Li is nothing but your phi I transpose m phi. So just go through the previous week lecture, you will find out how many modes you need to consider. Basically the rule is you just need to consider up to 90% of the modal mass. That means you need to consider the first modal mass, then you need to calculate the 90% of it, and you need combined all these modes like 5, 4, 3, 2. It's a iteration process. You just combine them and just check up to which mode that 90% mark is satisfied. Okay.
Yeah, thank you.
So that was your question, right? Or
Yes, yes, yes.
yeah, or else you have asked something else and I have to find something else. Anyway, so go back to our presentation. And for this question, just they have given the mode shape generalized mode, not generalized mode shape in the general term, n pi x by l. Now for one it will be different, for two it will be different. You need to calculate the modal masses. Here all the things have not discovered, not covered yet. Like for a multi-degree of freedom system, multi-degree of discrete freedom system, what will be that mass participation factor for each mode, you can calculate it. Just go back to the previous lecture, you can find it out. Now for the third question, a concentrated load of, so the previous question is clear, right? A concentrated load of 30 kilonewton. Dipan, you are from where?
Yeah, clear, clear. Thank you.
Yeah, no, Dipan, you are from where? You are which course you are currently pursuing?
This course only.
No, no, no. Like you are undergraduate student, postgraduate student, or a research scholar.
Postgraduate student.
Postgraduate student. Where? From where you are? Which institute you are from?
Anna University.
What?
Anna University, Chennai.
Oh, okay, 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 okay. Like here, yeah, I have seen you on my previous few classes, but like Bob, Nandalal and Sovik Chandan, they are continually attending the classes. That's why I'm asking you, and I know them like Bob and Nandalal. Okay. Now this question: a concentrated constant load again, 30 kilonewton is suddenly acting on the midpoint of a simply supported beam of mass is given 60 kg per meter. Length is given as 4.5 meter. The mode shape of the beam again in nth mode phi of n is given. Consider the uniform flexural rigidity, calculate the generalized forces. So it's also easy. What will be the generalized forces? The equation for generalized forces already you have derived for the continuous system. It's nothing but 0 to L phi n of x and the force x of t dx. So we have the load 30 kilonewton is acting on that system. So 30 kilonewton phi n and L by 2. So if you simplify this equation, you will get in terms of like the intensity of the force sine n pi by 2. So for the first mode you just need to replace n equals to 1. For the second mode you need to replace n equals to 2. For third mode you need to replace n equals to 3. So let's for the third mode we are looking for fn. That means what will be the f3? That will be 30 sine size pi by 2. Now if you have all the information about the forcing intensity, time point and all this part, you can solve it. uh, Sine 3 pi. Now what is the value of sine 3 pi by 2? What is the value of sine n pi by 2? That's why I am telling you, in all the questions you will encounter from this chapter, it's related to like you need to recall what is the value of sine n pi, what is the value of sine twice n pi, what is the value of cos n pi, what is the value of cos 3 n pi by 2. That will give you the confidence to solve. Like for the second mode it will become 30 sine twice pi by 2, that means sine pi, so that will be 0. For the third mode it will be sine 30 sine 3 pi by 2, that means sine 3 pi by 2 minus 1, so minus 30. For the first mode we can calculate like 1 pi by 2, so sine pi by 2 we know the value, so that will be only 30. So for the first mode, if they ask for the first mode n equals to 1, so f1 will be 30 sine pi by 2. Now sine pi by 2 you know the value. Now the second question related to it: a concentrated constant load of 30 kilonewton again is suddenly acting on the midpoint of a simply supported beam of uniform mass of 80 kg per meter, and length is given as 4.5 meter. So m bar is given 80, L is given. The forcing function f of x comma t is suddenly acting on this system. This is given as 30 kilonewton. EI is given. Phi n again this was given. So flexural rigidity, calculate the natural frequency for first and second mode. What was the equation for the natural frequency? Recall, omega n is equals to n pi by L square under root of EI by m bar. Now you have all the information. Just for the first natural frequency you just need to calculate omega 1 is equals to n is equals to 1, so 5 by 4.5 was the length under root of ei, that means 7 into 10 to the power 5 by 80, that will give you 45.59 rad per second. Now what will be omega 2 again? So n pi, n will be 2, that means 2 square 4, 4 pi square by 4.5 square under root of 7 into 10 to the power 5 divided by 80. That will give you 182.36 rad per second. Great. So by this way you can calculate it. So I already told you like this kind of question will come like the mass per unit length, the EI property, the modal information. Is not necessary to calculate this, but still you need to recall these parts how to solve it. Now again, generalized stiffness, they ask for generalized stiffness. Now I haven't covered that generalized stiffness, but we have the concept of this Kn in terms of MDF system. What was that? Phi n K or phi n transpose K into phi n. Recall for the MDF system, the modal stiffness. So for this also Kn for the continuous system 0 to L nothing but EI. We need to double differentiate the mode shape with respect to x square into dx, because phi n transpose into phi in integration it will become square, a double integration of the square. Now here all the information are provided. EI you know m bar, you know L, you know that forcing function, but the forcing function is not necessary. You know the phi of x. So what do we need to do? Phi double dot of x, you first calculate phi double dot of x for this, then you just need to substitute it. So here that will be the value. Now for the first mode, what you need to do? So Kn, first we have defined Kn is nothing but 7 into 10 to the power 5. That means the EI part, integration of 0 to L, 0 to 4.5, n pi by 4.5 to the power 4, and we have this square sine n by x by L square. Now for the K1, you just need to put n is equals to 1 for in this equation. For K2, you need to put n is equals to 2 in this equation. Now just solve it and you will find out the values. K1 is equals to 3.74 into 10 to the power 5 and K2 is equals to 5.89 into 10 to the power 5. Now I haven't go through that, so I have alternate approach to solve it. Say we know that the generalized mass and the generalized stiffness Kn is equals to Mn into omega n square. So from here we can tell that for this generalized mass for all modes we can easily calculate Mn equals to Ml by 2 easily. Now for K1 what will be that? That M1 into omega 1 square, K2 will be M2 into omega 2 square. So if you have the information about omega 1 and omega 2, you can easily calculate these two values, right? Omega 1 and omega 2. Or else you can calculate the omega 1 value and omega 2 value from your equation, like you have um, n square, pi square under root of yeah, by that formula you can calculate this, and by this way like K1 A1 omega 1 square, K2 M2 omega square, and that will lead to the same kind of calculations. 3.74 and 59.85, almost same. Okay, we have another question here from the displacement response. Okay, great. So before that we will solve this one. A simply supported beam of length 4.5 meter, length is given 4.5 meter, subjected to a loading if x comma t is equals to 10 sine 100 t kilonewton. Calculate the generalized force for the first and second mode. So again they have asked for the generalized force. Generalized force, we know if n of t is nothing but 0 to L phi n of x f of x comma t into dx. Now f of x comma t dx, we need to get it out from the integration, because here only the function of t is given, so it cannot be differentiated with integrated with respect to dx, so it will be constant. So take it out from the integration and we will have left with 0 to L sine n pi L by L. So after rearranging we will have for the generalized term fn of t is nothing but 10 sine 100 t. Now here we have L by n pi 1 minus, if we take it out, L by n pi 1 minus cos n pi. Now for the first mode, here cos n pi, that means cos pi 1 minus 1. So it will be some value 28 point something I have. You will have like 19.1 multiplied by 2, so 38.2 something for as per your data. And for the second mode it's 0 for your case and for this case also. Like I have changed simply here, instead of you have some values 20 or 30, and here instead of you have 4 meter of length I have changed it to 4.5 meters. So you will have two values like 0 and here 19 into 2 like 38.2. So that will be the correct answers for that question. Now we will left with one more question. Calculate the total displacement at the midpoint of a beam at t is equals to 1 second due to a concentrated constant force 20 kilonewton suddenly applied at the midpoint of the beam. Considering up to 3 modes only. Okay. So we need to calculate the response considering the up to n is equals to 3. That means we need to consider up to third mode set. So we need to calculate all these parts. So first, what do we need to do? We need to calculate the what is the generalized force acting on the midpoint. So force acting on midpoint, that means phi L by 2, that comes as 20 sine n pi by 2. On the previous question we have solved similar kind of thing. So displacement at the midpoint, what will be the displacement value? Recall y x comma t we have solved like n equals to 1 to n phi n of x and z n of t. So t is equals to 1. We have we need to have the information regarding the Zn, and we need to have the information about the forcing function. So for the first mode, what we need to do? For the first mode, first we need to calculate the F1, that means the generalized force at first mode. So 20 sine pi by 2, because 20 sine n pi by 2 was the general equation for it. So n is equals to 1, it will lead to 20 kilonewton. What was the m1 value? Modal mass already we have calculated, I think on the previous slide, or this m1 will be given to you. What is the modal mass corresponding to it? So 180 kg we have already calculated from the previous question where we have calculated the masses. It's a continuation question. Yeah. So from here you will get that 185 kg instead of 135, because here 20 kilonewton and 60, and on that question we have 80 and 20 kilonewton. So first what you need to do, you need to calculate that mn. From this equation you will have, okay, what will be the m1 for the first mode. So for the first mode you will have this 180 kg. Now w1 corresponding to that is given as 45.59 rad per second. Already we have calculated because it's the continuation of the question. And first mode, say phi 1 is 1. So at t is equals to 1 second, what will be the z1 value? Because we need to now have this generalized coordinates from the modal information. Now for the step or impulse loading, from the Duhamel integration, just recall what was the Duhamel integration term for the impulse loading? 1 by m omega n square 1 minus cos omega nt for the undamped free vibration or undamped force vibration case. And for this unit impulse, if we have the force Fn, then Fn by m omega n square 1 minus cos omega t. From the impulse response function, just recall that. And if we have the damped natural frequency, the equation Zn of t will look like Fn like am omega d e to the power minus zeta omega nt bracket 1 minus cos omega dt, like that. So we need to use this as the response of this step loading. Now if we have Zn of t, we can easily calculate what will be the Z1 of t, what will be the Z2 of t, what will be the Z3 of t, because we need to consider up to 3 modes: Z1, Z2 and Z3. So for Z1 we need to calculate this equation, we need to formulate this equation first, and then first put n is equals to 1 and t is equals to 1, because for the t is equals to 1 second we need to calculate. Now if we calculate that, z1 of t will come as 54.91 into 10 to the power minus 3 meter. Similarly for the second mode, if we look for f2, we need to calculate. So f2 will be this m2 180 kg, and okay, the modal masses, I think for this case all will be the 180 kg. Okay, midpoint, considering up to midpoint. So 180 kg for all modes, or 185 kg as per your data. You just need to check it. So I think that comes as 180 kg for each mode. Like I have solved it using MATLAB, so it gives me that that numbers. So please cross verify these things. Okay, so what will be the value of omega 2 we can calculate, and what will be the value of z of t for this mode we can calculate. That means we need to calculate z2 of 1. That means for 1 second what will be the z2. That means f2 by m2 omega 2 square 1 minus cos omega 2 is equals to 0. And for the third mode again we need to calculate f3. What is the value of f3, what is the value of m3, what is the value of omega 3. Now in general, once we have these three we can calculate zn. So we have now z1 of t, z2 of t, z3 of t. For three modes we have omega 1, we have omega 2, we have omega 3. Now easily we can calculate the responses. What was the equation for response? Y x comma t is nothing but summation of n is equals to 1 2 3, because we are considering three modes, phi n into zn of t, phi n of x into zn of t. So phi 1, phi 2, phi 3. So if we want to elaborate this equation, so this equation will look like something. Phi 1 z1 of t plus phi 2 z2 of t, phi 3 z3 of t. Now we have information about phi 1, we have z1, we have phi 2, we have z2, we have phi 3, we have z3. We can easily calculate the response. What is that? Y x comma 1. Why I am writing L by 2 over here? Because the load is acting at x equals to L by 2. That's why this L by 2, L by 2 and L by 2 um, mm, um, mm, notations are given. That means phi L by 2, phi 3 L by 2. That means at this midpoint, what is this thing? Because we are interested to have the response at that midpoint. Now, if you have this kind of questions, and if for this kind of questions it will be a continuation of a question where first you need to find out omega 1, omega 2, omega 3 for a simply supported case. Then you need to find out f1, f2, f3 for this case, and m1, m2 and m3 for these three cases. Now once we have all this information, you need to have zn of t. Now zn of t we have calculated it considering the undamped response due to impulse forces, just Duhamel integral and all this part, arbitrary loading part, if you see. And if we have that damped portion, then the equation will change like fn by mn omega d square multiplied by, we have that decaying envelope function e to the power minus zeta n omega n t 1 minus cos omega dt, like that. So by this way you can solve this kind of questions. It's quite lengthy. I think this big questions will not ask in your final exam, but for here for three modes, then they ask for the three modes. Maybe they twisted this question like this. Calculate the response for first two modes. It can be calculated like three questions will be given. First you need to ask for omega 1, calculate for omega 1 omega 2, calculate m1 m2, calculate f1 f2, and then calculate the modal response for at the midpoint for these two modes. So finally you need to add all these things. So here in this equation, or for the first questions, we have used phi n of x as a general mode shape. Now when we define that position of x is equals to L by 2, we can easily calculate what will be the value of this mode shape at x equals to L by 2, and for n is equals to say 1 2 3 4 5 6 and all of these things. So these are the basics ways to handle this kind of problems. Great. So that's all for now. If you have any questions you can ask me, or else we can conclude our session. Like for the continuous system, short kind of questions cannot be like prepared, but still this kind of questions maybe appear for your exam. Like k, they will not ask for the k, but for the f and m, and for particularly for omega, that means the natural frequency. Calculate the natural frequency for a simply supported continuous beam whose mode shape is given, whose mass density is given, and whose ei is given. Okay, this kind of questions. So generally we solve this kind of continuous beam problem using the finite element method. Okay, discretize it first, then we solve it. But still, we can solve the continuous system. It will be little, computationally heavy, but okay. For the concept, it's okay. Do you have the background regarding your finite element method? Do you have any background? FEM. Then only the continuous system and the multibody dynamics we can easily combine. Okay, no issue. So, do you have any kind of specific kind of questions or specific kind of queries, like we are at 11th week? Anything you can ask, or I have scheduled one extra class on 14th Monday from 10:30 to 12:30. So on that particular class, we will discuss all kind of questions may come. Like we will have 30 or 35 marks MCQ or MSQ question. I will go through it and precisely I will provide you the details. Okay. So that 2 hours will be dedicated to the question solving from first week to last week. What will be the things? What do we need to look for the final exam? Or for the next session, if you have any kind of particular requirements, you can tell me, so that on the next class I can address them. So do you have any kind of?
Actually, what I am telling, one sample question, what type of question may be asked in the test?
Yeah, on that day
Yeah.
we will discuss, and I will give you the 14th from 10:30 to 12:30.
14th, sir, whether it is holiday or not,
Yeah, it's holiday. 14th is holiday. It's Ambedkar Jayanti.
Ambedkar Jayanti. Okay, okay, then it is fine,
That's
sir.
why scheduled on that time 10:30. Yeah, otherwise it was not possible for me also.
Okay,
So we
very
will
good,
meet
sir.
on that day and we will discuss all possible kind of questions, and I will give you some relative question sets. If you practice them, it will be very easy to
Very good, very good.
attend the question.
Thank you.
Okay, then for now it's okay. So Bob, do you have any questions, or Sovik, or
I
else?
don't have any question, but 14th is a very, very busy day for me. But
Oh,
whatever it is, if I'm not able to join, I will still use the video, so that should be fine.
yeah, no issue. On the next class, you can clarify your doubts, and you will have the video lecture on the YouTube uploaded on that day. Okay, no issue.
Okay, all right. Okay, thank you.
Okay, then, if you
Thank
have
you
any
very much.
particular queries, you can mail me or contact me. So, thank you for now. Thank you, everyone.
Thank you.
Okay, thank you, sir.
Yeah.